Hello everyone, this is Luis Diaz at the Institute of Physics at the University of São Paulo. And in this series of videos, we're looking into a very simple model to illustrate the Bogoliubov-de Gennes Hamiltonian and how it relates to the many-body version that some of us, for particularly me, are more inclined and more comfortable with, which is the version in terms of number operators basis, a basis of number operators. So let's try to see how the two connect. So if we have the Hamiltonian as we showed in the latest video, we can essentially do a breaking, essentially doubling the number of terms in the Hamiltonian and formally write it in this form, this matrix form. The last video I forgot to add here that there's two constant terms that we forgot to add, which is this one, right? And this one. So I would have a constant here that would be something like that, but we can drop this because at the end of the day, we're going to do essentially disregard this constant, just a constant. And we're going to subtract the value of the ground state, so that the ground state in no case is going to be 0. So this is really not important. So the question is, as I said in the last video, our motivation is try to understand what are these fermion parity switches when you have a crossing in the spectrum. There's something like that. When the two of these Bogolibov levels cross the Fermi level, and this is from the site topoconnect.org. I strongly recommend this site, if you want to learn more about topological insulators, topological superconductors, Majorana fermions, and things like that. And as I mentioned in the last video, me and my students were discussing this paragraph, what means that when you have pair of levels crossing zero energy, you have a parity switch. So let's keep going, right? And let's diagonalize these two Hamiltonians. Let's take, for example, plug in numbers, right? I'm a numerical guy. I like to plug in numbers. So let's rewrite here our many-body Hamiltonian. Let's call it the many-body version, right? And I'll write the basis here, which I'm referring to, which is block diagonal in parity. So I have a state with 0 fermions, a state with 2 fermions, and 2 states with 1 fermion each. Something like that. And let's choose this, right? Let's choose E1 equals 1, E2 equals 3. That's the one I'm using. Actually, let's do it right now. Let's put a parameter here, alpha, right? I'll write this E2 that depends on this parameter alpha. I put 3 minus alpha, right? And E1 and delta are constant. They're 2. So my many-body Hamiltonian, I'll just copy it from here. Oops. Something like that. 0, E1 plus E2, delta, delta, all zeros, E1, E2. So let's do it this. Oops. How do I leaving these little dots behind. It's kind of bugging me. Let's do it like that. So I had 0 here. I have E1 plus E2. Let's do the case for alpha equals 0 first. So this is going to be 4, right? Yeah, this is going to be 4. And this is going to be 2. This is going to be 2. This is my first block. And my other block is just 1 and 3. Right? Now let's do the BDG Hamiltonian in a completely different basis. Actually, it's just a matrix form, right? So it's just single particle in a sense. This is one particle Hamiltonian. But notice, one particle means that these states are single particle, has only 2 states of single particle each. So I would have only 2 states in a sense, right? But here I doubled the number of states because of this trick that I did. So I have, some people call these the hole-like states, but anyway, let's do it. Essentially, if I had delta equals 0, the energies would be E1 and E2 plus this times this half here. So I'm going to include the half explicitly here, right? So that we don't forget. But this is 1, 0, 0, 3. Here is -1. This is -3. Here I have delta, which is real, right? This is minus delta star, but it's real, so this is also minus delta, and this is delta right here. So real, 0, 0. Okay. Now let's diagonalize both Hamiltonians and see if we can make sense of something, right? So let's start. I'm gonna pull a Mathematica script here, and this is this matrix, right? And I just diagonalize that. These are already put in terms of as a function of alpha. We're gonna play with that later. So if I order the states here, I would have something like that. 2 plus, well, these are not ordered. It's just whatever the diagonalization routine just put it to me. But these are the states, so 1 and 3, of course. And the eigenvalues of this block is 2 minus 2 square root of 2 and 2 plus 2 square root of 2. So there's 2 levels. So the lowest level here is this one. This is 0.85 or something, right? We can actually put a form. Let's do that. We can even do it, but it's 0.85 and at E many body of alpha, which in alpha is 0. Oops. And many body there. Yeah. Oh, sorry, evil. Yeah, this is minus 0.82. That's the one. That's the low. But I'm gonna set, and I'm gonna subtract this from the spectrum, and so that the ground state for the many body case starts at 0, right? So I'm just subtracting from from my from all the eigenvalues this number. So this is going to be 0. It's going to be 1 minus that. So it's going to be 0.2 or something. And we keep going. At the end of the day, we're going to have something like that. Let's put it right there. And I'm going to also put the E and B, which is already subtracted. Right? So 0, 1.8. So it's going to be the next one. And then, of course, subtracting. Essentially, I'm adding 0.82 to all of the other ones, right? Because I'm subtracting minus 0.82843. So essentially adding 0.2843 to this, to that, to that. So let's come back here and try to see what do we get in terms. This is our excitation spectrum, right? So excitation spectrum. So I have this 0. I have this first number at 1.82 something, 82.4, and 82.8. Then 3, 82.8. And 5, 6, 5. This is the ground state. So what does that mean? This is the excitation spectrum. So from our ground state, I can excite quasiparticles, right? This one and this one. This, as I said, has parity equals +1. Why? Because it's in this block. This is the ground state, right? Remember? So the ground state is this one, is in this block. The other two eigenvalues of this block is 1 and 3. They're the middle ones, so it's 1.82, 3.82. These have parity equals -1. But the ground state and the most excited state each have parity equals +1, right? This one and that one. And this is parity equals -1, -1. So from here to here and from here to here, I'm exciting one excitation, right? One single quasiparticle, if you wish. So I have two quasiparticles here. And now, if I go from here to here, I am on the same parity. I have two quasiparticles. Now, if you do the math, 5.656 is exactly 3.82 plus 1.828. You can even, you can reach that conclusion here, essentially. So here, this is this state where I have two quasiparticles in the system. That's what the excitation spectrum tells me, right? So in other words, if I add these two numbers, I should get this. So this clearly is a two quasiparticle state. So okay, this is the information that I get from the many-body Hamiltonian. Let's call it that, like that. Now, how about let me get rid of this. I already talked about the excitation spectrum here. Let's do this. Let's get rid of this line. Now let's see what we get from the Bogoliubov-de Gennes part of the Hamiltonian. This kind of, okay. What do we get? Let's put in a different color here. Let's put it in magenta, for instance. Now, if I calculate the eigenvalues of the Bogoliubov-de Gennes, I have something like that. So let's put it the numbers here. Oops. Let's plug in the numbers. I have something like that. Minus, oops, a little bit more. This, and this is kind of 0. So I have minus 1.91. Notice that I'm already including the minus 1.914 minus 0.914 plus 0.914 plus 1.914. This is the BDG spectrum. And how does it relate to this thing here? Well, here is a single particle spectrum. This is one particle. So to do the excitations, I need to populate this level. But notice, I cannot put 4 fermions in here, as if these were just single particle fermionic levels. Now, for every pair of levels is a single fermion. So I have to occupy them 2 at a time. And remember that since I have these negative energies here, meaning that when I populate a negative energy of level, essentially this population is part of the quasiparticle energy. So I'm always populating them in pairs, right? So for instance, if I populate this guy and this one, what's the total energy? Is this 0.914 positive that I have? And this also 0.914 that I have to go from my vacuum to this level, right? This is, I need, to create a particle here, I need to spend this amount of energy. So the amount of energy for one particle is plus 0.914 plus, well, the absolute value of the other one, 0.914, which gives me what? 0.9 is 1.8, 1.828, which is not coincidence, is essentially the same value here, 1.828. Now the other excitation that I can do is, let's erase the other one, is to put one here and another here, right? So what I'm doing here, I'm doing 1.914, another one, right? So I don't have this one. I'm just creating an excitation in this level. So I have to create this pair, right? Since all comes in pairs here, which is 1.914 plus 1.914, which is 3.828, which is exactly this energy here, right? And of course, if I add these two, now I have the system fully occupied, then I get this other one here. So these two excitations, of course, I have only one particle. These all have parity -1, while the two particle excitation and the zero particle excitation, so this is 5, 6, 5, 6, have parity of +1, and of course 0. I realize I'm out of time again, so I'll wrap up this discussion and discuss about the crossings that were, the parity switch crossings in the next video. I'll see you then.